Hello, it's dumplet here. Here's an item on algebra. Find all functions f mapped from the set of real numbers to the set of real numbers such that f of x plus y plus f of y equals 2y plus f of x for all real numbers x and y. Credits to the Art of Problem Solving community for this item. As usual, pause this video if you'd like to give this item a try, but if you're done, let us dive into the solution. Now, whenever we have a functional equation, our first instinct is to maybe have a guess as to what the answers are or what the functions are. Now, here are some of the lists of functions that we technically try. Well, we can try to see if f of x can be constant, like 0 or generally c, or can f of x might be linear, x plus c, or even generally kx or kx plus c. Or f of x might as well be like 1 over x or something else that we want to try, depending on the given function. Now, you can try to manually verify some of these, or sorry, manually substitute one of these, but generally speaking, x plus c works in this case. So if you're going to try f of x equals x plus c, you can substitute into the given equation given, and you're going to see it's going to work. So we might want to think, what properties does the function f of x equals x plus c have? Now, in fact, f of x equals x plus c, it's bijective. So it's injective, so it's 1-to-1, and surjective at the same time. So maybe we want to prove that the function is either injective or surjective. Now, let's start with the fact that it's injective. And in fact, that's the only thing that we need to solve this item. A little bit of spoiler alert, but all we have to do is to prove that it's injective first. So let's try to do that. So let's suppose for now that f of a equals f of b. All right, so if you want to prove that a function is injective, then we're going to suppose that f of a equals f of b, and then we want the result a equals b. So let's try to do that. So this is our claim. We're going to claim that f is indeed injective. Now let p of xy over here, p of xy, let this be the equation. So if I make the substitution x equals a and then y equals b, I'll get the first equation here. And on the other hand, I'm going to make the substitution x equals b and y equals a, and I'll be able to get the second equation over here. Now, let's try to compare the terms you see here. Now, the first of the pair of the terms, so the left-hand side of both equations, take a look at the underlined term a plus b plus f of b, and the other one b plus a plus f of a. Now, since we made the assumption that f of a equals f of b, this f of b is the same as this f of a. So these two underlined blue expressions, they must be equal. So f of this blue expression must be equal. Now, on the other side, we have this f of a equals f of b. Well, that's obvious because we made the assumption that f of a equals f of b. So it makes sense that f of a should equal f of b because f of a equals f of b. Now, we can just simply use the addition property of equality, and then we can conclude that since these two equations are true, we should be able to get that 2a must equal 2b. So you can try to subtract the two equations or whatever, and we should be able to get that 2a equals 2b. Well, if 2a is indeed equal to 2b, then divide both sides by 2, we'll be able to get that a equals b. And we've successfully proven that the function f in this case, it should be injective, since if we made the assumption that f of a equals f of b, then we're going to get that a equals b. So that's very nice, because in the next step, we'll be able to use the injectivity. Now, let's make y equals 0. Now, why do I want to make y equals 0? Because if y is equal to 0, well, this would be gone. So I'm technically comparing to f of some things. Now, since from the injectivity, we have if f of a equals f of b, I can just equate whatever's inside those functions. So if f of a equals f of b, then I'll be able to get that a equals b. And that's pretty nice, because if I made the substitution that y here equals 0, then f of x plus f of 0, I don't really know what f of 0 is, but at least we know it's a constant for now. And this is equal to f of x. Now, since I have the injectivity proven, I can simply compare whatever is inside those two functions. So since f of x plus f of 0 is equal to f of x, I should be able to get that x plus f of 0, this equals f of x. And this is from our claim that f is injective. Now, f of x here, f of 0 over here, it's just a constant. So let's just make it some value c, because we know it's a constant because f of 0, we substituted 0. So we can technically say that f of x should be something of this format, x plus c, for some real number c. So the c here is just the f of 0 that we made. But what's interesting is that if I substitute x plus c directly to this equation, which is the given equation, we can see here. So let's just say that f of x equals x plus c. Well, f of y over here becomes y plus c, and then the f of x over here becomes x plus c. Now we can do one step further. F of x plus y plus c, so that's technically f of x plus 2y plus c, so we have two y's over here. So this is equal to x plus 2y plus c, and then the 2y here just becomes the 2y here, but f of x plus c it's going to become x plus c plus c. And what's interesting about this is that both sides of the equation are the same. So this is technically a 0 equals 0 scenario. So we've only known so far that f of x should be of this format, x plus c, for some real number c. But it seems to be the case that it will work for all real numbers c. And from this, we can already make the conclusion that f of x can be any of the function x plus c. So f of x can be x plus c for all real numbers c. And usually when proving when answering a functional equation, this would typically be at the start as a claim, but to avoid any spoiler, I just put it at the end. But usually in Olympiad math fashion, we would start with claiming the function and then proving that the function actually works, and that's the only function. But anyways, we have f of x equals x plus c for all real numbers c. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye!